Can you guys see this? Yes.
Yep.
Okay, cool. I do like seeing all your logos, and I am quite happy that you guys are very interactive, so please be. How many people here, actually? It's a nice small, oh, fuck, 43, shit. Okay, so now, I was hoping it would be 10 people. Okay, so this is what we're talking. So I'm very unprepared, guys, other than having a cool idea of something I was reading about. Actually, a couple of months ago, I was reading through. So I'll give you the background quickly. So I am reading a book. It is about Haskell, and it's quite cool because, like, although I've been using Haskell and languages like that, like PureScript, etc., for a little while, nothing really seriously. Um, there's probably a few fundamentals that I skipped over. I just looked at and there's something called the state monad, which is like I've always understood how to use it, how to use the state monad, and it's like, oh, okay, cool. It's quite a cool structure. And we'll get into more detail, and I'm not going to talk to it from a Haskell perspective, but more from a execution perspective, which is probably what's more interesting. And so a few months ago, I went through the exercise of implementing it myself, so building my own state monad, as opposed to using the one that is provided by the standard library in Haskell. And actually, it was such a cool experience of going through it. And I built it in a way, it was like, I took it from first principles. I was like, let me just write some code in a particular way. And then let me layer the, refactor it and refactor it and refactor it over time and then actually what popped out at the end was the state monad. And it was like, oh, okay, cool. So now I went and filled in the missing pieces for myself, which, and it was, for me, it was quite a cool experience. And so then I started to think yes, this is quite awesome actually to see things at this level. And then I thought oh, how could I, I'd love to tell people, but nobody knows Haskell and nobody really gives a shit about Haskell. And then I was like, but actually, fundamentally, I could easily do this in JavaScript. In fact, I could write this in almost any language other than, I could probably do it in Python. And I just thought wow, wouldn't it be cool actually to just go through that process again, in another language, which is maybe more accessible, like JavaScript, and see what pops out. So I haven't really prepared much other than having, so we might be Googling as part of this, especially around the types, etc. But, and I have no fundamental objective other than wanting to just show you guys something which I found quite cool and taught me a few interesting things. Of course, we're going to start with why would you want to be more of a functional program? And I think we know these benefits are all true, and I'm not going to hammer on any of them, other than going yes. So we can all agree, I hope, or maybe not, but you will eventually be able to agree that functional programming definitely has benefits for all of these reasons. Yeah, there's probably more, as well as just being seeing things from a different perspective sometimes. Like Machin's talking about this, it's bit him in the ass before in JavaScript, and it's okay, but you probably bring a very either object-oriented view to the world, and so no matter what language you pick up, you're always trying to probably mold it into your own world view of things, or the way you internally model things. And there's nothing wrong with that, and object orientation is absolutely a very good way of modeling the world, 100%, but it's not the only one. And so functional programming brings maybe a different paradigm. It just expands your mind, it gives you another tool that you can go to. And the cool thing with it is it's very much a style. So it's not it's not like a technology. Functional programming is not a technology. It's a style. It's the way I write something. And being able to change your style sometimes can be a good thing, because depending on what it is that you're solving, an OO style or an imperative style or a functional style or an aspect-oriented programming style, there's lots of different styles, can be sometimes very useful, can simplify your problem a whole ton if your style works well for that type of problem, right? And so it's definitely worth learning more functional programming stuff, definitely. But one of the issues for me certainly is the more I learn about this domain, and it's for me, I like going quite deeply into them, is yes, I buy all these benefits, until and like I'm convinced, they sound amazing, right? And then you're like, okay, so what languages would I, would be the best to accentuate this style? And then it's these languages here on the right, and like probably all of them are like, yeah, okay, so these are great for weekend warrioring, but like, are you really going to write any of these things in like project code or production code? And it's like probably a whole lot more difficult, right, to go and say, yes, I'm going to use Haskell and some web framework to write my API, and then I'm going to use pure script on the front end to build my front end. It's like, yeah, probably most people would say, yeah, it's probably not a good idea. Like, first of all, you're not going to find the skills, and et cetera, et cetera, et cetera. So there's many good reasons to go and learn these languages. Probably there's a whole ton of good reasons why not to use these in the real world until they become more mainstream, which I do believe that they will. Like, I do think Haskell and Scala certainly, and PureScript are like, they're pretty amazing. And I think the more you understand them and the more you evangelize them with your friends and in the community, when people's level of like understanding of them start to bubble up, I do think that they are very powerful, and they have like certainly a good place in the world. Absolutely. So yeah, so that was my first slide. I actually made these a while ago, so I don't even know what's coming up. So let's see. So one of the so I'm not here to like make a case for either way, other than like, let's do a cool experiment where we try and implement this like highly pure functional structure called the state monad, and let's use a language like JavaScript, and let's like all go along for the journey and see how good or how crap it looks at the end of the day. But let's just go through it. And I think as part of it, there could be some interesting things that we learn about functions, and maybe like some different ways of looking at functions other than just being these things that you call that do stuff or return stuff. You can also use them in a way to create control, like flow control, and to be able to weave an idea through multiple lines of code, etc. And that's exactly, hopefully, what we'll get to with the state monad. But one of the important things before, so there's a couple of like foundational things we need to start with before diving into code, and hopefully we'll spend most of the time looking at code or writing code. Is one core difference for me that's quite important to understand before we get into, and this maybe speaks to like the why thing here, is generally it's good to recognize the difference between imperative versus reductive execution. And these are two very big words, and maybe some of you know what they mean, but for me, very simply, is like an imperative. So here we're talking about execution. So this is how a program executes. So when I write code, we can make some assumptions about how it executes based on what like mechanism of execution it uses. So when we talk about imperative, because imperative is an execution mode, is an execution style, I suppose, you could still have object-oriented code that is based on an imperative execution style, right? So it's not as opposed to OO, it's not opposed to functional either. Imperative is how a program executes, right? So if we look at the example on the left, actually we can just look at that, is in an imperative style, the way a program executes is it starts at the first line and it executes it, and then it goes to the next line and then it executes it, and it goes to the next line, executes it, and it goes to the last line and executes it. That's what imperative. So imperative has this natural, it's almost assumed that the program will fall down to the next line, right? Of course, you could have like an if condition or like a break statement or a return or something which changes the execution, but by default, things just go to the next line. So it's like a list of statements, statement after statement after statement. And probably 99% of the time when we look at code, we probably make the assumption that the execution will happen in an imperative way. It goes from top to bottom, right? Does that kind of make sense? So we'd look at the first line, x equals 5, and what the program would do is it would create a piece of memory somewhere, the size of an integer or something, whatever types, so I haven't put types here. And it would call that x. It would somewhere else keep a little table of names of variables or something, and it would then the next thing it does is it will take the value 5 as an integer and copy it into that memory location. And then we haven't told it what to do next. It's kind of done. And then it goes, okay, nothing else to do. Let me drop to the next line. Cool. Y equals 3. Okay, create a space for 3. Does that make sense? So imperative code, right, it has this implied sequencing to it. Interestingly, though, that's not the only style. There is another style of execution called reductive execution, and this is made famous by languages like Haskell or PureScript and others, which are based on not the Turing type of because when we talk about imperative, it's actually in history, it goes all the way back to this guy Turing, who invented this machine. I don't remember what it's called, the something machine. And what it did was it did stuff in sequence. It did the first thing, then it did the next thing, then it did the next thing. And so, and through that we built this yeah, the Turing machine. Exactly. Oh, sorry, Bhavesh, you've got your hand up. Do you want to say something? Check, you can actually see your own hand appear on my screen. How cool is that? So you can talk. You are very soft.
Is that better?
Yes, better. How's it?
Okay, cool. How's it? I wanted to ask, does SQL fit into the reductive execution or imperative?
Sure. That's a very good question. It could be. I'm getting a weird echo. Do you want to mute again? So like, so when you say SQL, can I write programs in SQL? So do I go like statement by statement? I think SQL, like the whole program is the select statement, right? So the way it resolves the select probably is reductive, actually, if I would think about it. But I don't know. Does anyone have an answer to that?
I don't know the answer, but I think it depends on whether you're using transactions and some of the other capabilities that it has.
Yeah. So I suppose the sequence that like select or insert statements happen would be imperatively run. Yes. Yeah, I would say so, because it always goes like from statement to statement. Like if you were in a transaction, as Jared says, definitely it's implied that it would fall down. But
to me, it's both. You know,
could be, yeah, because I think
like
within a statement,
you can do a
reduce
statement.
it. Yeah,
Statement.
But I would think it's reductive as well, because it looks at your where clauses and stuff first before it actually runs your select.
Yeah, it's
That's what I
reductive.
was
It's a
thinking.
statement.
Yeah, possibly. Yeah, exactly.
In a script,
so you
it goes one by one.
Yeah. So you can see that it's like, it's interesting to, it's like, it's not always obvious that imperative style is right. So to talk about reductive comes from another branch of computing called the lambda calculus. Some other guy, maybe Alan Church, I think was his name, is the dude who, along with Turing, I don't know if they work together, but they both came out with different means of building like these theoretical computers. Turing's one was very imperative, so it's like just given a list of statements, it would execute statement after statement. You can imagine like punch cards or like through tape, it would just execute, you know, statement after statement, like add this thing to a register, then take that register and add it to some other register. We just do them in sequence. So that was like Turing's fault for creating that style. But there was another guy, Alan Church, I think is his name, who was more of a mathematician, and he said no, computation can be done in this different style. And so if we had to reread the thing on the left, was it Clean Church? Oh, okay, it could have been, yeah. I think it was someone Church. Yeah, I thought it was Alan Church, but that's Alan Turing, right? Alan Turing, yeah, Alan Turing, Keen. Okay, yeah, I believe your Googling powers. So the way the lambda calculus would, Alonzo Church. That sounds more familiar. Anyway, it's enough. It's not important. You can Google it. Well, the way he would do it from a it's more of a mathematical way of getting to the answer. So a program that looks like this imperatively really would just look at the end result, and it would say, oh, you're looking for x plus y. So it would go, well, what is x? And then it would go and look at x, and it would say, oh, x is 5. And what is y? Oh, y is 3. So I'll just return 5 plus 3. That's the answer to this program, right? So it's reducing itself to the answer. And in that scenario, like this Z line would actually never even be executed in a reductive execution thing. Because we can see, and even in the imperative style, you'll probably have the compiler saying, hey, like Z is not used. So like, what are you doing? But of course, when it actually, you know, what I'm intending it to do is for it to go X times 2, you know, like in this order. So you'll often see in a reductive, in a language that executes in more of a reductive style, you will often see these things written in a different style, less of an imperative style, and you'd see something more similar to the one on the right, where my whole program is actually x plus y where x equals 5, y equals 3. Do you know what I mean? And then z equals this other thing, and that's cool, but nobody will ever know about it. And so that's a different way of executing stuff. So are there pros and cons to them? Yes, absolutely. So imperative is like it's more easy to understand the order that things will happen. Of course, there'll be like line after line. With reductive, you have the potential that your program could be more efficient because it can leave out whole chunks of execution that don't make sense or that are never used. And so quite often you could even you could build a language which is called lazy with a reductive style. A lazy language is one that will only execute lines of code that are really needed. It will just leave out all the other stuff that's not needed. So if that makes sense, which is quite an interesting idea. Of course, the downside of reductive execution is you don't know in what order the stuff happens, and so your programs are never this simple, right? X plus y, where x equals 5, y equals. You may have other stuff in this thing, like write something to a file, or write something to the console, or read something off disk. And it's quite important that happens, that you read something off disk probably before you use that value. And so sometimes ordering is important. It is like often very important, especially when you have IO or you have stuff like, like if you wanted to go like console.log here, dog or something. It would be cool if that happened before this happened, right? In a reductive execution model, this would never execute because console.log doesn't do anything. It doesn't add anything to the result of the program, which is x plus y. And so in a lazy execution environment like that, log would never happen. And so that's a bit weird, if that makes sense, right? So it's good to recognize these two execution modes. So the problem is, so something like Haskell, PureScript, Elm, a whole lot of functional languages are very much in this reductive execution mode, and so that's very cool. But what if I was trying to write a program where actually the order of what I was doing, I wanted to be explicit about, and I actually want these things to happen in a particular order, maybe because I've got IO happening or whatever, or maybe just because I want my program to be read semantically, in this ordered kind of way. And so you can of course do this in a functional, in a reductive style. And so here's one example of how you could do that. So here's that same example where we are now going to ensure that that x equals 5 and then y equals 3 and that z equals x times 2 before we return the x plus y, assuming that that we're in one of these like functional reductive modes, right? And so it looks a bit nasty, but if you can see the thing on the right, does this make sense to anyone? Does anyone understand what that thing does? And this is actually JavaScript, guys.
Yeah, it's callback functions.
You could call them callback functions, but I'd rather just call them functions, right? They're not being called back; they're being executed. It's not like it's not a deferred execution. They're executing immediately, right? Because it's like here's the first line is x. So it's a function, yes, it's a function that ends down there. So I colored them to make it easier. There's the function there, which is being executed with the value of 5. So x will equal 5 by the time I get to this line. And then in that line, there's another function there, which is being executed with the value of 3, setting y to 3. So x equals 5, y equals 3, z equals x times 2, and then x plus y. Right? And so this actually will, someone's got a horrible echo. I can bust you now.
Okay, but here in the case of the x plus y in the z function,
yeah,
is it taking the value of the multiplied x that's being passed into z, or is it taking the value of x from the outside function? So my question is,
yes, it is. Yeah. Well, what is this? Well, read this code, right? It's exactly the same as this code. What x is that?
No, but well,
this x is the same as that x is the same as that x, right? So this x is the same as that x, which is the same as that x. right? So the scope of this x is that x up there, which is 5. So that x would be also the same scope as that x. This is a parameter, right? It is what z is equal to. Z equals x times 2, right? It's not changing the value of x. We're only introducing new variables. So that x is the same as that x, which is also the same as that x. This x is that x, and this x is that x, right?
So then,
I mean, it's like mind-boggling to look at this, but this is absolutely a valid way of, in a functional style, making sure that stuff executes in a particular order, right? Would you agree or no? Should I pull this into a? So first of all, maybe before we look at understanding this, we could just check if everyone is comfortable with this notation. Is everyone
Tom,
comfortable with this notation?
could I just ask quickly then, this would make sure that x times 2 runs, right? So this isn't being lazy loaded anymore, or lazy running.
No. Yeah, no. Yeah, exactly. Yeah. So what I'm saying is in a reductive style, I can make a program that semantically executes in the same order as an imperative program.
Cool.
Does that kind of make sense? Because it's forced. I'm forcing it to execute in this order through these like nested functions, which is a bit odd.
Yeah.
I agree. I'm not saying that we must do stuff like this. I'm just saying here's like the worst way of doing it, right?
I mean, why not, Tom?
Yeah,
Just the
exactly.
chat
Right?
there.
Why not? Because it's fun. So quickly, is everyone comfortable with this? So wait, there's a few things we must know about JavaScript. So we know this style, so I can go const, like say I've got a function and it's like add, I can write it like this, a and b, and that is a plus b. Is everyone comfortable with that notation? So I can go console.log add 1
Yes.
or something. So this is
So-
called an arrow
so-
function.
Yeah,
Yeah.
but in this case, A, B are the inputs of the function. The arrow says what the arithmetic operation is or whatever you're running for that function.
Yeah.
And then the name of the function is add. So
Yeah.
whenever I see the brackets, that's the input. And then
Yes.
the operation run on the input. I'm happy with
Yes.
it. And then when you call add and pass in the parameters, then it'll just bring back the result.
Yes. So the magical part is that part. This defines a new function with no name that takes two parameters, I suppose you could call them, and it has this implied idea of return. Do you know what I mean? So if I don't put open-y, scopy, brackety things here, then it implies the word return. So they're functionally equivalent to const add equals function a comma b, and then open bracket return a plus b. These two adds are the same. Add 2, add 1, right? Do you agree? Is everyone comfortable with that notation?
100%.
and this is where stuff gets maybe even more scary. So let's take this. Okay, we're gonna write potentially a different then do. And then we may need to rename this thing. But let's see if we can refactor this even better, because we're starting to make some good progress. So let's make a program for. We get vars coming in. That's fine. We're going to start there. Let's actually just take this first line and see if we can do this better. So what we know we want is at the end here, we want to almost hide this vars thing. Like we know we're going to get an underscore. Like we want the x's and y's to come in for sure, x and y, and the underscore, that's fine, when we're doing nothing. And we almost want the vars like implicit. We want to like pull them out. So it's like, well, what could the first parameter to then do then look like? It's like, okay, its first parameter could be a function which, given a vars, does something, right? And so what does it do? It still returns this, like, what do we compute on the one side, which is undefined, and what does it do on the other side is it takes, sorry, I think I can just drop that bracket, is it does this little update there. Yeah, that's fine. And yeah, so this is our first refactoring, which is like that. So I'm just getting rid of that vars there, because that's like, it's always present, right? And so we almost refactoring this first parameter to then do, which is that one, vars. Instead of it being a vars, we want to rewrite it like in this way. Let me just rename this to then do x, because we're going to rewrite then do, a better then do, which is going to now hide this vars thing. So this is a new then do. And what is he going to look like? He's going to go like then do equals, sorry, const. Let's rewrite him. So it's like the first parameter here is a function which, given a vars, wants to return a list with, which wants to return a list. Yeah, which will be the undefined and the new state. And then the next parameter to it is, let's think. Yeah, so it's like we want it to be an A to a new vars, kind of like that. I'm just giving a method signature. This is not actually JavaScript. So let's just go kind of like this. Then do is a function. Its first parameter is really this, is like a function which takes a vars, returns a list with something, and that same state again, right? Its second parameter will be, let's think, it's like that same thing to a function which returns an A to a vars, which is quite interesting. Yeah, and the result of this thing must be a vars to an A comma vars. And this is like, okay, so I'm starting to get into like a bit of monady world here, but effectively it's like, given a function which can compute something and return a state, like that's my first parameter. So this is almost like a state transition. It's a function that, when given some state, will give you something and a new state. Does that make sense? So that's what vars is. Vars is our state, right? So given some state, I want to do something, like calculate something or whatever it is, and give you a new state. Then our second parameter is a function given a value and a state. So this is actually execute that state, vars. What are you saying there? Is that Nabil? Talk, Nabil?
Look at the picture.
Oh, did you paste something?
It's a vase.
Oh, vars. Oh, very clever. That's not how you spell it. Good point. Good point. So let's just go with this. I think we'll get back to this signature, because I'm even myself getting a bit confused. But let's rewrite this thing down here to this very simple signature, right? So here we're going to be, it's a function which is given a state. We're going to do nothing for this one, but we want to update the state, right? So we're going to split vars, and we're going to go x is 1, y is 2. And because we're doing nothing, so we're getting rid of effectively that vars there. Sorry, these are tabbed funny. So effectively, we're getting rid of the vars there. So the next function is also a then do. So this tells you a little bit about then do. Like then do is taking a state again. And then here we're going to say, okay, so what do we want to calculate? We want to get vars.x, I think. We want to look up vars.x, and we do not want to change the state on this one. And this must give us x, something like that. So here's like the pattern for looking up x, right? The next one is like, well, now we want to take x and we want to add 1 to it. We want to take that x there. We want to add 1 to it. We're not going to manipulate the state. So I've got tabs on. And that's going to give us another x, correct? And then we want to, now that we've got the x, the result of x, we're not going to do anything. We're not calculating anything. But now we want to update the state. Was x is x. I think I should be there, right? Which will give me then nothing on that update. Let's just see. Have I got bracket issues? Does this look wild? Is anyone following me?
Mostly.
Tom, don't you need the vars x plus vars y at the end, line 43? So
line 45. I need to actually return something here.
Yeah, on line, yeah, but I think it's line 33. You just need to.
Oh, sorry.
That,
oh,
right?
yeah,
So,
yeah.
yeah,
So we haven't implemented
one,
that.
yeah.
Yeah. So
I
okay,
think
so
followed.
I've like minimized my. Yeah, we just going into gymnastics here. Let's just try it. I mean, it's fun to explore. Just some ideas of using functions in a slightly different way to like, let's write an imperative program without using an imperative style, right? Let's write it just using functions to force this. So I've rewritten a worse program, but I think we get the idea here that it's like, okay, then do is going to take some parameters. It's going to calculate nothing. It's going to set 2 values inside state, producing us nothing. Then on the next iteration, we're going to just look up x, giving us x, and not mutating the state. On the next function, we're going to calculate what is x plus 1. So yeah, we've kind of merged the idea of looking up and calculating it, but at least we've separated them into 2 different lines, not mutating the state. And then on the next line, we're going to calculate nothing, but we're going to mutate the state. So I've kind of separated that look up, compute, store that we had there, right? Look up, compute, and store are now 3 different operations, I suppose. Does that kind of make sense? We're just going to return x. So hopefully at this point, x is 2, but we haven't actually implemented this then do function yet, right? And that's what we were like, we need to implement up here. So let's try and.
Can I ask you quickly? So in my mind, like we're building that pipeline.
Yeah.
And whenever you say mutate, it's not really the old-fashioned mutate. It's create a clone of the old state, mutate, set the new field on the new object and pass that through.
Yeah.
But that's what's weird about the pipeline, is that you like abstracted that part away now. But it's this pipeline view. Is that the right way to think of it?
I think so. Yeah. So I think there's some rules in functional, like you can't mutate stuff because that doesn't work in a reductive execution style. You can't reduce stuff if things can mutate because we must know universally what x is equal to, because we don't know the order that things will execute. So x must always only have 1 value. It can't change its value through the execution, right? Because if it does, then the order of reduction is very important, right? And so that only works in an imperative style. Mutation of variables only works in imperative programming, right? But that's like a different discussion. That's a more theoretical one. I'm just trying to like, let's see if we can do wild stuff with JavaScript here, and see what we come out with actually. And let's see if we can even make this better. So let's try and figure out what the hell is going on here, because what we've done is we've kind of just moved the vars that used to be there over there, and we've kind of made it, put it on this side. So this implies that the first parameter to then do is actually, this is it here. It's a function, right? So we can rewrite this then do to look like, I don't know what did we call the first parameter? We called it vars earlier, but I think it's called something else. Let's just call it like left. It's the parameter that's the first one. Maybe I'll say first, call it first, the first parameter. And the parameter, the second one there is the second parameter, right? And it's like, well, how do we implement then do? So we know that this first parameter is a function given a vars. But wait a minute, where does then do get its, and it itself must return a,
don't you need that original state somewhere to feed into that? So imagine you're going to go
that's what
first,
I'm
and then you're
thinking.
going to pass in that state first, open bracket, and then pass in the state, right? On line 39.
Yes. It's a good point, but however, then do itself could return a. Let's think about what does then do return actually. And I've put the method signature up here because this is the gymnastics part. Is this actually correct? Yeah, I think it is. So actually, what then do must return is itself a function which, given a vars, will give us the a and the vars. So this effectively is weaving. It will like weave the vars through itself. So sorry, let's actually, let me just change the values here. So given an a, I want a b, and that must produce a state, which is a b. Yeah, so that a is different to that a. This is the signature of a state transition. So it's like, it's effectively, yeah, it's hard to explain. Let's just write it and see what happens. What we actually want to return here is a function that, given a vars, is going to execute the left. So let's just call it first with vars. So that's first with vars gives me an a comma vars, a new one. So let's go const a comma vars, and we can call this like, let's just give this a different name for now, vars1. Right, so we're executing that function with this new one, which we've created. So it's like no one passed us vars. We ourselves are returning a function which, when given a vars, will execute the first one with that vars. Does that kind of make sense? So here's this is a little bit of a wild thing here, because then do itself now is no longer executing a function. It is returning a function which, when given a state, will return the new state.
Tom, that's like the carrying sort of.
Oh, sorry. So yeah, where you see two things like this is just saying this is a function which returns. I mean, you could imagine the word return like that. It's like, but you can have multiple arrows in line. Yeah. So like this function returns a function which, when given a vars, executes this stuff. Let's just keep going. So this is effectively taking the first parameter, which is this, a vars to an a to a vars. It executes it with this new vars. Then we want to, now we've got the a, which we can now feed into the second function there, giving us and the vars, and this new vars giving us a b and a vars 2, because we want to return a function which is going to return a b with a vars. Yeah, so we're going to get the b and vars 2 by executing the second function with the a. You agree? So that's that first a, and with the new vars as its second parameter, which was that one, so the change state, and then we want to return b comma vars 2, basically. Something like that. Yeah.
Yep.
I think so. So program 4 now no longer, so if you think about what it returns, is it's no longer returning the answer. It's actually returning a function which, when given a vars, will return the answer. So actually, like, I know I'd put this in earlier, and I thought I felt like I wanted to, and here's kind of the reason. Like program 4 now is actually follows that same pattern of then do. It's like it is itself a function. So I can now drop that vase there. Does that make sense? Because it is already, the vase are being provided up there, which is a bit wild, but a bit weird. But let's see. Let's see. Maybe we can unpack this if it works. So program 4 now is a function which, when given a vase, yeah. So program 4, does this looks right then? Yes, I think so. So I would give it no variables. Second is not a function whose return value is not iterable. Why? Second. So second is, let's just see actually. So second is that. It's just a function. Oh, so wait a minute. A function given an A calls then do.
But the then do you're calling is expecting 2 parameters, and you're only passing an empty object as the first parameter.
Explain it. What line are you looking at?
If I look at const program 4, the very first call is you're calling then do.
Yes.
And then do is expecting a list.
Then do
And
is
then,
a function.
so if you were to map the function's signature to the parameters being passed in, vars would be first, but there's no second being passed in.
That's first.
And similarly, so when you're calling program 4, the open curly bracket, close curly bracket is being passed into the first vars, unless I'm mistaken, but that's the way I see it.
Isn't this is the first parameter to then do?
Yes,
Correct, which is first.
Yeah, so that's first, which is a function which, when given a vase, will give us an A and a vase 1, right? A and vase 1 first. Given a vase will give us A and vase 1, right?
By evaluating that function, Tom. So, right, so that's your line 39. So it will evaluate it straight away and then give us that partial result. Okay, yeah.
Yes, I think so. Which will give us A and vase 1. Then this is our second parameter. This is where we're going wrong, I think. The second parameter is a function there, which, when given something, anything, the A, which is the same as that, must return a vase to a B to a vase, B and a vase, which is the same as then do, isn't it? So that is, yeah, so second, execute with A, i.e. the undefined, because we know A will be undefined for the first line, right? A is undefined, so we execute this with undefined. Yeah, and that gives us, and we know here we're doing a then do.
So Tom, the error is on line 40 at the end there, right? Is it that vase 1 second call that you do after that second A call?
Oh, that one.
So
is that the problem, or I'm not managing to read the error? Yeah, it is there. You see the little underscore there is for the vase 1 call.
But are we trying to say second A returns another function which you then just invoke with the vase 1?
Yeah, I think that it's right, because then do, I think, because then do itself returns a vase to a list, right? A vase to a list. So it is okay. So this then do into that then do should be okay. This is probably the issue here, is this X. I think,
yeah, that X may, yeah.
Because so what our program 4 needs to be at the end is a function that when It needs to be at the end a function that when given a vars must return vars.x. Something like that.
But Tom, why is it vars.x and not vars.x plus vars.y to be the same as your line?
Oh yeah, I've just cheated and not done the y part because I'm lazy.
Yeah,
because Tom was just unpacking the X calculations.
I'm just doing the X part.
Okay, cool. But, yeah, but then that's it. Yeah, because okay, let's try that, Tom. I think that's right.
Maybe like that.
The list, yeah.
Yeah, there we go. So it's like, of course, the final, the final thing returned must also be a function that, when given a vars, does some compute and gives us the updated state, right?
Yeah.
So all we're doing is X. Yeah. So interestingly, now so when we run this thing, now we go like, oh, we get the answer, which is X is 2. And it also prints now these things, right? Which is like, okay, that's cool. So we've kind of woven we've separated these things, but and the cool thing is they're kind of composable at some level, because that pattern, we're starting to see there's an emergence of this pattern. There it is again, and there it is again, right? It's this, like, given a state, I can give you a something and a new state. And we see that pattern like often repeated, like there it is there. So you could almost start to say, well, then do is like, given some state transition and a function that goes from an A to a state transition, I can give you a state transition, right? So like, if you look at that function signature, they're like pretty composable. So then do's can be joined to other then do's, because look, the first parameter to then do is the result of a then do with a function that is like something and a state transition. Do you know what I mean? So it's like, I've almost said here, I'm like writing Haskell now, but I'm saying that a state transition is actually like a function from something to a something, and from a state to something and a new state. Do you know what I mean? And now, like with that pattern, this is like at some functional level, you can see composition happening here, because it's like, oh, given a thing. So it kind of means that I can start to then do things
like, give me
together to
so
each other.
I can change the states.
Yeah.
Kind of equates the state transition.
Yeah. And if you think about it, like, that is right? So
yeah,
it's like, given a state and a function which will do something and return a new state. Oh, that's a state transition, right?
Yeah, exactly.
You know what I mean? And so, yeah, I'm just trying. I mean, this is not JavaScript. These type signatures are not JavaScript compatible. Maybe in TypeScript we could actually get to something where we create something like the knowledge of a state transition, which is a typed function like that. But I think we're there. Are people mostly hanging on? Because now we can just go, oh, we can make this even better. Anyone still hanging in there? Let's write a program 5. Anyone still hanging in?
I'm super excited to see how this ends now.
I just need to sit through and go step by step over that function, because I think I understand how it works, but there's obviously a little bit of confusion. But I'm sure if I just sit through it, because I understand the concept around it.
Yeah, this is a bit wild. This is hard to.
Also, in that example, your then do is not functional, because you've got constant
because of this.
returns.
Yeah. And I said we would cheat a little bit. Of course we could make it worse, and then you would understand it even less. But I think maybe this is probably the best way to show it. Yeah, you're quite right. We can write this in a more functional way, absolutely. But I'm cheating because it's okay. It's my tech session. I'm allowed to cheat. So anyway, so now we can say, okay, fine. So we can see, like, there's patterns again here. So if I look at this and I go, okay, well, what is this thing doing? This is kind of, so actually let's write the program correctly, right? As Luke pointed out, we are still cheating here. We're only dealing with X. Let's deal with Y. So there's the lookup of y, giving us a y. And with y, we're going to multiply it by 2, I think, giving us a y. And then we're going to calculate nothing, and we're going to update y with y, giving us nothing. And then finally, we're going to have a something which is going to go calculate x plus vars.y and change nothing, right? Something like that. I think that deals with, should give us our 6 again. I've probably got compile issues here. Oh yeah, there's brackety issues. Too many. There we go. Okay, cool. So we get 6 now as the first element. So, but we can start to see patterns happening here. We can see, okay, this is like storing of x and y, if that makes sense. And actually, this is probably also crap. Let's do this properly. Like on the first line, we should be storing x, and on the second line, we should be storing y. Does that make sense? Like we should try and do one thing per line. I don't know, in my crazy world. So there we go. We're storing x in here. So it's like, oh, look, here's a pattern. We can see a pattern here that when we store stuff, like this line and this line, they're almost the same other than this little part here, right? Or maybe the splatty part. So it's like, can we refactor that out to make that more explicit? So let's write a new little function called, actually, let's just take this program 5. Yeah. And go like, what if we called it, we made a cool function called store, and in store, we go actually just like this. We want to go store an object. That makes sense. Did I have bracket issues? No, yeah, something like that. So it's like, oh, can we make a function called store, which takes an object which does this for us? And it's like, yeah, we freaking can actually. It's like so simple. So let's write the store function. It's like, well, store, we know looks like this, given a vars and a, given its first property will be like, store is something which takes something to store. So it would be like, what do we call it? Like x. It must return a function which, given a vars, will do undefined, but then it will splat. How do we splat? Do we, can we just splat x here? I suppose we could. Something like that. So there's a function called store. So I probably have to say const. Is there compile issues here? Yeah. So like there's a function called store, which we give it an object. We're going to call it x. Maybe I shouldn't call it x because it's going to confuse us. Should I call it a? No, that's also confusing. I'll call it k. So we store things called k's, and it's going to return us. It's literally like I've literally gone and pasted like, what does that do? And now I can rewrite it and call it store. Do you know what I mean? It's literally the same pattern as that one, right?
But this store one, it's taking the variable off the stack, your argument, and putting it into this list that's growing, right? Is that so that object?
Well,
no.
List?
So
no.
it returns a function which does. So when we store stuff, we definitely compute nothing, and what we do is we mutate vars with whatever you told us to store.
So in essence, when you say store, you basically put as a parameter in the store open bracket x colon 1 close bracket.
Yeah. Look, there it is.
Yeah,
Okay,
exactly
so
like
it's
that.
It's a
yeah.
clone and merge sort of storage that I'm seeing, right? It takes the old state and creates a clone and then merges new state into it.
It does exactly this. It splats vars, then it splats whatever k is. So it overwrites whatever k is. So it splats vars, then it splats k. So anything you pass as k will be splattered in over the top of vars, but not mutating vars, creating a new vars. Does that make sense? I've literally taken this line.
So basically, all we've done is taken that second part of the vars splatting that we do after undefined and storing that in a variable, right?
Okay.
So, in a function.
Yeah. So I've rewritten that line there,
and
and just made it a function called store.
Yeah.
This part. It's not called store, but it still is a function which will return a vars and give us that list with no compute, but the mutation built in.
And the difference here is that you're not passing undefined and vars as an input parameter.
Yeah, because stores
You're
is like
only
implied.
passing the
compute is
variable
implied.
you want to store.
Yes, exactly. Yeah. So I've just made it like nicer, right? It's a nicer way of doing it. Because like we were seeing those emergent patterns of going, oh, this is just storing a y. So it's like, oh, cool. Okay, so we can now rewrite that as store just that y, please. And it's now no longer a list that we're dealing with. Everything else stays the same. So, well, let's keep going. So then what about this line? What is this line doing? This is like a fetch of something, right? Or a lookup. What should we call it?
Unstore.
Fetch. So
Unstore.
fetching. What is it?
It's the opposite of store, so unstore it.
Read. It's called read.
I'm silly.
Read, right? Fetch, read. Let's read it. So it's like, well, read what? We're going to read a k. We know that we must be a function which returns a vars. And then, well, what are we going to do? We know that we read it into this first position of the list. So it's like, well, what is it? So it's like we need to look up the k element of vars. Oh, actually, so read is interesting because it could be like there's no way of there's no way of passing when I do the read, when I rewrite this and I'm going to go read, I want to go like .x, right, of this vars thing. But there's no way of doing that. I can't just go .x. JavaScript's not happy with that. It has to be like a given the vars, give me vars.x, right? So actually my first parameter is a function which is going to pick up that thing. So then my first element is k applied to vars, right? Right? And then we leave
Tom,
vars
so
unchanged.
that's true here, but what's interesting is if you use the getter syntax, then you could actually go,
Oh, cool. Tell me about the getter syntax. How does that work? What can I write?
Is that TypeScript maybe?
Yeah, it could be. Yeah,
Sorry.
yeah. So if I had TypeScript, I probably could go .x, which is a function which, given an anything, will give me that anything.x, right? But I can't do that in ES6, so I have to write it like this. So there's my looker upper, which is k. So it's a function applied to vars, and then we know that we do nothing with vars. So when we read stuff, we don't mutate vars, so we just pass vars again, right? So there's our read.
I'm just curious as to how you're going to differentiate your read function to your compute function, because it's the same parameter in the list, right?
It could be. Yeah, it could be. So read is always a function given the state, whereas compute doesn't have to be given the state. So remember that when we're computing stuff, look, we never access vars here. So let's just write compute. So it's compute is the k, and we know we must return a vars, and it's like, well, then what is the first parameter? It is just the value of k, right? And vars. So compute is different. It's less powerful than read. So with read, you could also write compute. So compute
because if I look at the example of, let's say, where you compute, where you're reading y, you say vars, and then as the first element you say vars.y, right?
Yeah, I could have easily.
Then the very next one, but then the very next one, because yes, I understand the separation.
Yeah.
The very next one you say vars y times 2. So how do we differentiate vars.y is a read method versus y times 2 as a compute method if we were to try to separate it into separate methods like you're doing now?
Well, this one has no reliance on vars.
All right, is that how you...
Reading needs a vars and compute doesn't.
Very
It
nice.
just uses what's available, which is what's in scope, right? It could, I mean, I'm not saying we can, of course we can cheat here, and here I've captured it. So it's like compute, given a k, return a vars, where we just give that k. There's no k executed on vars. You know what I mean?
Actually done computation in compute. The computation happens just before you call it, that parameter you pass.
Yes.
So you could wrap that x plus 1
in there
and pass it to read. And pass it to read.
Yeah,
and
yeah, I know you could. Yeah, absolutely.
And you have one less function.
Yeah, absolutely. And I'd be cheating. Yeah.
No, well.
Yeah, it doesn't matter. I'm just, it's interesting, right? So here, here, and now we're storing again, right? So this is a store of x equals x. So we can go store. And actually, how cool is it to use Kieran's syntax here? We just say store x, and that gives us a nothing. And then here we're reading so reading must be a vars to a vars.y. Sorry, and then we can kill all this. And we know when we read, yeah, we get given that thing back like that. This is a compute.
You're missing a comma after the read, a close bracket.
It is a comma, I think. Yeah.
Oh, it is a comma, yeah.
Yeah. And then this is a store of y. Something like that. Oh, sorry, store is a function with a y, giving us a nothing. And then our result is like something like that. And in fact, actually, at the end, we could just go compute, right? Because compute itself is a vars to a k of vars. Now we probably got bracket issues.
Yeah.
There's closed bracket issue there.
And 67, same issue.
Oh, yeah. Check out that shit, Uggs. Yes, look at that.
It is beautiful.
So beautiful. Right? But it's like, did we do something amazing?
Almost looks like Lisp with all those open and close brackets.
And it makes sense, you know, so that's the beauty of it. Not only is it gorgeous, it's also like, useful. Yeah.
I mean, there is an argument.
It's like, it's literally the opposite of me.
There's an argument to be had that 40 odd members of this chat took an hour and 40 minutes to write that code, whereas the top code that we're basing it on took you what, 3 minutes to write?
Yeah. But it's just, so it's interesting because, so now this is pure functional. 100, this is a pure functional program. This is indisputably pure functional. So they are absolutely, we've written this in a way where there is no mutation. There is an imperative semantic to the way that it executes. But actually, this is a fully reduced program, if you think about it. So
well,
it's quite interesting. We've gone into inception here because we've taken an imperative language and we've written something pure functional, which reflects an imperative style.
Well, we didn't rewrite it as then do function, have we? Because then, in essence, then until that's rewritten, then
well,
this
I'm going to leave that. You said you struggled with this, so you can rewrite this in a pure functional way, and you totally can. Of course, you can. So, in fact, what this tells you, what this could tell you, is that everything imperative can be written in a pure functional way, because we've just kind of proven it. We've written an imperative semantic program in a pure functional way. And so this is like how Haskell would do it. Interestingly, actually, we can go back to our cool slide here where we had an example Haskell program. And look here. So if we look at this thing, it's like you could maybe recognize some of the things like, oh, look, it's updating x to 1, updating y to 2. Then it extracts x as a thing called x. This is called a binding. It's binding this like value called x to the value of get x from that state. Then compute x plus 1 and bind it to another thing called x. Then update x to x. Then extract y, then compute y equals y times 2, then update y, and then return x plus y. Do you know what I mean? And actually, like, here's the JavaScript version of that. It's basically the same. The difference with Haskell, just for interest's sake, is there's just like slightly nicer syntax where, and actually it would be really cool if JavaScript had this. Maybe it does actually. Do you know if JavaScript has? So if I look at this line. Maybe this line is probably the best, like the read or the compute. One of these where we're assigning something on the right, like that x is being set to what is x plus 1, sorry. It would be cool to take that line and rewrite it like x equals compute x plus 1. Do you know what I mean? Like I want the x on that side. So if I could write then do in a different way, I could like maybe infix then do, or create an infix operator which would put that x on that side on the left. Do you know what I mean? That's all that Haskell is doing here. It's like the x is equal to extract get x. So it's putting the x on the left, which makes this actually read nicer, because if you think about, we go compute x plus 1 and then put it on this thing on the right, when actually we kind of wanted to go x equals x plus 1. We kind of expect the x to be on the left. Do you know what I mean? From a syntax perspective. And so Haskell really converts this to that. It binds
can I just check something with you? Like with a trivial example where it's all in memory, I think it's very difficult for me to convince myself that like, yeah, this is worth the hassle. But when I think of this as like, okay, externalize it as a pipeline, maybe a Kafka stream or something. Yeah. Now I can take what you've written on line 63 onwards and pipeline it.
Yeah, totally.
I think it starts to make more sense that like, because you can't mutate somebody else's memory, therefore that's not even an option. Therefore, you are going to have to do this anyway if you said, okay, can I have it in Kafka?
Yeah,
so
totally.
Is that a fair way to like?
Yeah, it's a very fair, it's a very good observation, because if you think about the way that this thing executes, it's really up to the way then do handles it, right? So then do can actually be like, you can have a network-based then do that might take this thing and execute on a different machine. It could run these things in parallel. It doesn't really matter. So it still looks like a very imperative program, but the actual execution of how it actually ends up running is up to how then do chooses to run it. So it means that it's switcher outable, right? I could have a different then do which doesn't invoke it now. You know, it might ask another machine to invoke it or whatever, right?
Or it mutates its own state internally, right? But that's up to then do to decide. Yeah.
Exactly. Yeah. So like we're abstracted from the runtime. So it looks imperative.
Hey Tom, can we see the output from program 5 though?
Oh, sorry. Yeah.
And then while you do that, the discussion with the update and the sets that we were discussing, it sort of reminds me of assembly language in a way, where you got the very low level single operations.
6 billion humans.
Exactly what I was thinking. Watching.
So there's one function we're missing here, because so Peter, you asked me to run it, and it like still doesn't give us 6, right? It gives us 6 with something and then the new updated state, right? So the cool thing is here we could take program 5 and compose it back onto program 5 if you think about it, because remember it keeps vars. So like interestingly, this is composable. So if I think about, maybe I write a program 6, and program 6 just does a then do of store of Tom hello or something, right? Maybe that's all that program 6 does, just stores Tom hello, right? I can kind of take program 5, which does this other stuff, and I can compose it with program 6, because I can run program 5 and then run program 6 kind of together. Does that make sense? So I could go program 5 after program 6. You know what I mean? So they're kind of composable in some sense, I think. Second is not a function. Yeah, of course it isn't. And it's like, yeah, this does nothing other than compute undefined or something, right? Something like that. And it's like, check that out. So we've got, I don't know what's going on there. Something nasty is happening. But we're almost able to like quite easily share state between programs through composition in this sense. I can, because they kind of share the same state store. So it's like, I've created this idea of global state, you know what I mean? That is shared between programs. I have no clue why it's destroying things. Some things fucked, but I don't know why. Maybe compute broken. Doesn't that compute K with Mars? I don't know. But like that's another interesting thing, is that these functions can even though they don't mutate state, they can be composed together so that they look like they do. You know, the same way that then do composes together like this. Of course, entire programs can be composed together in the same kind of way, right? We are just missing one function called run, like the run function, which is given a function, which is one of these. So like the output of given a vars, given a function, yeah, given a, I don't know what to call this actually.
It's
It's like a
return K, right? Yeah.
given a program. Yeah. It's like we want to and a state probably. So like a starting state. Let's call it start. Given a start and one of these state transition things, execute that state transition with the start, but then also just return us the first element because we just want that first element. Does that make sense? And so that's probably what run looks like, something like that. I've probably buggered it up. So instead of going like executing program 5, I can say, oh, run with a starting state of nothing. Please run program 5. Something like that. Assignment to constant variable, buggers, equals, oh, wait, this is wrong. Like that, right? Yeah. Does that make sense?
Mm-hmm.
And I mean, whether however you want to run this, I mean, it could be like start and program if you like. Yeah, it doesn't have to be like partial application like I've done it. Maybe you want to do it like that. Run program, or maybe it's the other way around. Probably that makes more sense. Run program 5 with this starting state. Right, it doesn't really matter how the signature looks, but that was a missing function because previously it was popping it out.
So stacks became lists, arguments became captures, something like that. There's like some interesting high-level magic that replaced your lower-level stack variables in this approach, kind of. Think
Yeah.
so, Tom? Yeah.
Yeah, I think so. So the interesting part here for me is the capturing of state inside these little functions. So like I have a function called store, but like it always returns a state it always returns a state transition. This is a state transition. Remember earlier we said a state transition is a function which given a state will give you something and a new state, right? That's the name of a state transition. It's always a state transition is a function. It's not an object. So we've actually captured the idea of a state transition in terms of a function. It's not an object, right? Meaning that we can then define lots of interesting state transitions, like a store type of thing. So a storing of a K gives us a state transition. A reading of a K gives us a state transition. A compute of a K gives us a state transition. A running of that's why I would have preferred to have kept run in the other way around, because then it also kind of follows that pattern. So running with a start state gives us a sort of a state. This is no longer a state transition. It gives us a value, but it's like it takes something which it takes a starting parameter and a state transition, executes that state transition, and gives you back the result of it. So it's quite interesting. It's just like here's an interesting way of, and then of course you could refactor this to be even simpler. So you could say const, I want a store and read, right? Which is like given a K and so like, no, it wouldn't be a store and read. It would be like a read and compute, right? A read compute store, actually. Compute store is like, okay, so give me the K that you want to read, then the L that you want to compute, and then the KLM, and then an M, which is the store, and I'll give you back a state transition where I implement those things, right? Which would be like,
and you just
K of
compose.
vars, and then that one together. I could actually compose them. Yeah,
Just
that's
compose
actually
from the-
that's actually 100% right. I should be composing them. I just go, oh, okay, so we're gonna store K, then do So we do a then do of store k, you know, blah, blah, blah. Compose them like that, right?
Yeah.
And so it's like, oh, look, I'm creating a higher level thing. Should we actually try this? We do a store of k. Does read compute store work? Yes, it does. So we know that when we store stuff, we get nothing. And then we're going to do a compute. So should I call that R? We're going to read that, we're going to compute that, and we're going to store that. So we're going to, what am I doing here? Just storing. No, read. We're going to go read. Oh yeah, that's going to have to look like that. So it's going to be read of R. That's fine. Giving us a something. I'm going to call it Rx. Then I'm going to compute. And actually, I could make this compute cooler because maybe compute wants that R thing in it. I don't know. Compute C. We'll see it later. When we compute it, we're going to get Cx. And then we're going to then do store of S. And storing we know gives us nothing. Oh, I think we just end with a then do, like that. Is that right?
So that last bracket, I think the last bracket underscore you get rid of, right?
So I've made single.
Yeah, single.
I think something like that.
No, sorry, I'm wrong.
Does that make sense? Read, compute, store.
And you need to pass in what you compute, your little computation somehow.
Yeah, so it's going to be weird, like, because when you store, you want to probably call S with CX, with whatever you computed, right? And when you compute C, you probably are going to want to pass in RX, because that was what you read, but you'll see that now. So if I go cons program X equals, let's just go read compute store. Yeah, read, we can just call it read compute store. Our first parameter is the R, the thing we're going to read. So it will be a function like v to v dot tom or something. So we're going to read something called .tom from this thing. Then yes, right? So like we could actually do it like this. And then the second thing we're going to pass is what we want to compute. But we know that it will be the tom from the top. So whatever we read up there is going to be passed as the t there, because that's what we're doing there. It will be t. And then we want to go like, how do I uppercase stuff? To uppercase of t. I think I can do that, right? So that will do the compute. And then the store will give me the uppercased version. And we're going to store you. I think we have to splat this like that, right? Program X. Now we are getting crazy, dudes. So we're going to run program X, but with a starting value of Tom set to dog.
I love it, Tom. You say now we're getting crazy. Only now.
Yeah. Oh, sorry, I've got that.
Like all of a sudden, it's just crazy out of nowhere.
To uppercase is not defined. How do I do this?
I think it's to upper.
To upper.
With a capital U.
Yeah, I think.
Or is it dot to upper? Dot to upper.
It's usually string dot to upper, I think.
Like that. Not a function, X.
No, you're right, Tom. It's to uppercase on the string. It has to
like
be on
that.
the string. To uppercase, U and C are capital. So you're right.
Okay, now it says underscore is not defined. Where is that? Over there. So on the store, read compute store, where are we doing this? There. Oh, yeah, that's fucked. Can't do that.
Yeah.
Then on the store.
It's just like a function that does nothing. Wait, no.
So it must call store, and then that will give us nothing, correct?
Should it not return the stored value back? or
Yeah,
not?
it needs to always return a one of these, right? So a vars to a.
So it's just underscore. Is that right? It's a do nothing.
No, it's a do nothing. Yeah, it's a
Yeah.
do nothing. So what would it be? It would be. Let's just write it out. Given a vars, I want undefined and vars, right? I think this is like that's definitely a pattern we.
So look at your line 82, now 83. That
Yeah,
last one after your store was like the last compute.
Yeah,
But
so
you
it
don't
could
wanna
be
do- yeah.
just compute undefined. You know, like do nothing at
Yeah.
the end.
No.
Undefined. Yeah, so read compute store doesn't do anything. You're quite right. Yeah. So let's not make it run. So we will well, let's make a run, like we'll just call something called run2 or something, and this one doesn't get the first element, so that we can go run2 and we can see what the state looks like. Oh, it fucked it up. Run compute store. Why? Because we store s of cx. Compute store. So store is this u. Compute that to uppercase would give us the u, and we want to put u in there.
Shouldn't the last line, instead of that compute of undefined, be a read of the final?
Yeah, it should be, right? Yeah, because it's like a funny program, this read compute store with the undefined. So that explains that undefined. But I was kind of hoping that the state change would show at least something where u is equal to Tom in uppercase. That's what I was hoping for. Because we are calling store with s. We call s on cx. Cx is what we computed, which is the two uppercase. So Cx should be so this is where we can get nasty, and we can put in brackets, and we can go console.log Cx maybe, right? And then do this and put the word return. So now we can debug it a bit. What's my issue here? Too many brackets. What am I broken? Oh yeah, of course. Oh, bugger. Return that, but actually these brackets. Can I do this actually? Yeah, I can't really do this because it's like needs to be like that. I don't know, guys. Look, dog, it is uppercased. Screw you, man. So store s of cx. I don't know, but you get where we're going here, right? It's all beautifully simple.
So my question is, if you are approached, or if you approach a stack that is not functional, at which complexity level do you decide it's worth it to switch it to functional, as opposed to going, it's going to take longer to switch it to functional, just leave it as object oriented and we'll deal with it?
No, I don't think what I'm saying is I'm not promoting this. I'm just saying it's good to expand your mind to see this, like alternate ways of doing things using functions. Like we've done something pretty magical with just functions, actually.
Yeah, look, I'm not saying recreate Haskell using JavaScript, but just as a general, do you have a thought or an answer on when it's better just to leave it as object orientated, as opposed to trying to fix or better it by making it functional?
Well, does it work in its current style. I think you always have to have a good reason to rewrite anything, right?
I was going to say, there are people who would argue that object-oriented doesn't work in general, but
yeah,
And
it
then-
depends on your view and whether it fits the domain that you're trying to solve for, and the amount of like complexity, right? There's like necessary complexity. I think they call it like essential complexity versus, what is it called? Essential versus, someone will know. Essential complexity versus accidental complexity. So these are two interesting things to know about. Accidental complexity comes from like potentially technology choices and architecture choices, and then essential complexity comes from the domain. You know, if you're building something for a very complex domain, you should expect that there will be an essential amount of complexity in the software as well. So you want to, like, essential complexity you can't reduce. It's like based on the domain. If it's a very complex domain, you're going to have an amount of complexity equal to the essential complexity of that domain. It's the accidental complexity that you want to aim to reduce, which is, which is like maybe the choice of technology or the choice of architecture or the choice of something, where it's like you've added that complexity when it was unnecessary. You know, it was accidentally added. So I sometimes think of things in terms of that. It's like, think of the domain. If there's a ton of accidental complexity in a system, then it maybe does warrant a rewrite. If you're finding that it's not delivering on its promises, right? But you'll never replace essential complexity. That will always have to be there, no matter what language or style or technology you use. It's always going to be there.
So just to extend the point, when would you decide to use functional programming over procedural or object orientation or whatever the case may be?
So there are some good reasons. The one is like with a functional with a lot of with good functional languages, you can often take them forward to like to mathematical proofs, so you can know with certainty that something works, which is quite cool. So you can have like provably correct code, not tested it. We tested it and it works, but we proved it's correct. Doesn't, given these inputs, we will always get these outputs, which is quite interesting. And so if you're in a domain where that's important and you need provably correct code to be written, you can't do that in an imperative language. It's just not possible. The Turing approach to computation is not mathematical, so you can't mathematically prove anything about an imperative program. Whereas with one built on lambda calculus, you can. There are ways of proving mathematically that something is correct, which is pretty cool. So that tells you you have a much higher opportunity to build correct code with function, because at some point with imperative there's a limit. You can't get to the point where you can be 100% certain that something is correct. You just can't. Even if you've got like 1 million test cases, there's probably 1,000,001 test cases. There's like one other test case that you forgot about, right? And there's at no point can you know with certainty that you've written enough test cases. You know what I mean? Whereas with maths you can have that. It's not to say that all functional programs are provably correct though. No, it's still you have to design things in a way that deals with proof. So that's one interesting thing. So like if you're writing something that's absolutely mission critical, then maybe a functional style is interesting. There's also I think Luke was talking about it earlier, where if you're building something that needs to be highly distributable, a functional style will definitely help you along that path, because it will remove the bad things you can't do in a distributed world, like mutating state, causing side effects, all that kind of stuff. So it makes those things harder, so you tend to rely on them less. You know what I mean? So I would say in general, functional programs are easier to distribute, meaning they can run on more than one core, they can run on more than one machine, more than one node, all that kind of stuff. They generally distribute better, if that makes sense. Just because there's rules fundamentally underneath which disallow mutation. Also, the ordering that things run is less important in a pure functional style, because we have that reducing type of approach to execution. The order of that things run is less important, where it's very important in imperative world. So you can't take an imperative program and say, well, run these first 2 lines on that machine and then these 2 lines on that machine. It's like, no, you can't, because the order that they run is so intrinsic and important to the program. Whereas in a functional world, it's not important. These can run on that machine as long as it's got the inputs that it required, and these can run on that machine as long as it's got the inputs it requires. You know what I mean? It was quite interesting. Any other questions, guys, before I say goodbye to you all?
One request.
Can you put? Okay, go for it.
Sorry. Can you send us the code?
Yeah. So maybe
Same question.
I'll make a repo. I'll commit it into a repo. Is that cool?
You read my mind, Bhavesh.
Awesome.
Awesome. And then Martin, this is your job. You need to make that not this.
Why, thanks for giving me homework.
Yeah, this is your homework. Any other questions? Nothing.
This was very informative. I really enjoyed this session.
Cool. Yeah,
Thanks.
it was gymnastics, am I right? I knew it would be. It was a bit
Brain gymnastics.
Yeah, brain gymnastics. There we go. And then someone can find the bug in Program X where it doesn't to uppercase the Tom properly. And there's something fucked here. This is broken, I think. It's my guess. I don't know. All right, guys. Have a cool afternoon.
Cool. Thanks so much. Cheers, guys.
Dudes, ciao.
Bye.
Thanks, Tom.
Cheers, guys.